let me tell you about a couple more examples of conditioning of the arrival of new information, and then we'll talk about conditional probability traps. Okay, let's go back to the Monty Hall game. So the Monty Hall game. Okay. And remember, so the contestant is at door 1, the prize is at one of the 3 doors, door 1, 2, or 3, and Monty opens either door 2 or door 3 in the case that the prize is behind door. So if the prize is behind door 1, so this is the outcome 1, 2, this is the outcome 1, 3. Okay, and here he has to open door 3, so this is the outcome 2, 3. And here he has to open door 2, so this is the outcome 3, 2. Okay, but now I'm going to add a twist. So, the prize is randomly placed behind a door, so this is 1/3, 1/3, 1/3. Okay, but now I'm going to add a twist, which is that Monty, if he has both doors available to open, prefers to open door 3. Okay, so in this case, he has only one door to open, which is door 2. Okay, in this case, he has only one door to open, which is door 3. Okay, but here he prefers door 3 to 2. So 2/3 of the time he will open door 3, and 1/3 of the time he will open door 2. Okay, so that's just, Monty has just a preference. If he can, he'll open door 3. Okay, now, exercises for you. Prove, show, compute the probability to win by switching. Okay, and this is, we already computed it, and the intuitive argument is he wins whenever the prize is behind either door 2 or 3, if you switch. Okay, so let's compute the probabilities. 1 times 1/3 is 1/3. 1 times 1/3 is 1/3. Now we have 2/3 times 1/3, which is 2/9, and 1/3 times 1/3, which is 1/9. Before they were 1/6, 1/6. Okay. Now you still win in these two outcomes by switching, and so the chances of winning by switching is 2/3. Okay. Now I'm going to give you some additional information. You're playing the game, and Monty opens door 2. Okay. Monty opens door 2, and I claim you should be jumping up and down for joy. Why? Okay, so let's think about this. Well, Monty prefers door 3. Okay, because if both doors were available, he prefers door 3. So why did he open door 2? He opened door 2 probably because he couldn't open door 3. He prefers door 3. Again, why wouldn't he be able to open door 3? Okay, he wouldn't be able to open door 3 if the prize was behind door 3. So he opened door 2, okay, likely because he would have rather opened door 3, but the prize was there. So you should be jumping up and down for joy. Okay, and now here's the exercise. Compute the probability to win by switching, given that Monty opens door 2, and show that this probability is 3/4. So, when you didn't have this additional information, your chances of winning are 2/3, when you didn't know which door Monty opened. So, in other words, at the beginning of the game. But now that you have this additional information that Monty is going to open door 2, your chances of winning have gone up. And that corresponds to it confirms the intuition that I gave you, that, why wouldn't he open door 3? It must be that the prize is there. Okay, so here's another, and this is a more subtle example. Okay, so, I'm gonna show it to you, and then I'm gonna ask you to read the text, and which analyzes this example very carefully. Okay, and if you can analyze this example on your own, then you basically understood probabilities and how to update probabilities when new information comes. So let me call it a case of 2 boys. Okay, so you have 4 friends, A, B, C, and D, and here's what you know about them. They each have 2 children. They each have 2 children. Okay. Now, let's ask the question, what are the chances that their 2 children are boys? What's the probability of 2 boys? Okay, and now here we have to make some assumptions. And we're going to make the assumption that, having kids is like flipping coins. Each time you have a kid, it's like flipping a coin, a fair coin, and half the time it's going to be a girl and half the time it's going to be a boy. Okay, so asking what are the chances that, anyone has 2 boys is exactly the same as asking you flip 2 coins, what are the chances you get 2 heads? Okay, so that's 1/4 times 1/4. So this is 1/4. Okay, now I'm going to give you additional information, new information. Okay, new information. 1. So in this case, that A has at least one boy. A has at least one boy. So what is the probability now that you have this additional information, the probability of 2 boys, given at least one boy? Okay. So that's the exercise. Okay. And I'm going to tell you the answers. Okay. Now, you might think, well, what's changed? You know, look, what's changed is that you have this new information that A has at least one boy. Okay? And now you're asking, what are the chances of 2 boys? Here, you didn't know anything else, and you were asking, what are the chances of 2 boys? Okay. Okay. Now, okay. So let's see if I can give you the intuition here. So if you know that he has at least 2 boys, then what are the cases? The cases are that A has a girl followed by a boy followed by a boy followed by a girl, or a boy followed by a boy. Those are the three, cases to which you are narrowed down to, when you know that A has at least one boy. You know for sure that it cannot be girl. Okay? So of these 3 cases, one of those is 2 boys. So intuition suggests that the probability of 2 boys, given that you know that you have at least one boy, you have 2 cases, boy, out of 3 possibilities, boy, girl, boy, so you might suspect it's 1/3, and indeed it's the case. But, you need to be able to get that using conditional probabilities and the method that we have, given you. Okay. So that's, if A has at least one boy. B, let me give you some new information about B. B's older child is a boy. Okay. So now, what's the probability of 2 boys? Given that older is a boy. Well, how is this different from that? So that's subtlety of information. This is a subtly different statement, subtly different piece of new information to A has at least one boy. This guy, B's older child is a boy. So let's look at the scenarios for B. So if the older child is a boy, then there are only 2, we've narrowed down to 2 scenarios. Either the younger child is a boy, and then you got a boy, or the younger child is a girl, and then you got a boy. So it's girl, boy, or boy, boy. So you have 2 options, and one of them is boy, boy, so one might suspect, intuition says that this is a half. Okay, and indeed, compute the conditional probability using the method that we prescribe and get a half. That'll show that you know how to compute conditional probabilities. This is worked out carefully in the text, okay, in the chapter. 3, new piece of information. Okay. You were on a walk and you met C. Walking with a child, walking with a boy. Okay. So what is the probability of 2 boys given that you met a boy? And you might wonder, what? How is this any different from the first situation where you told me that A has at least one boy? Isn't this exactly the same? You met C while walking with a boy. Doesn't that just tell you that C has exactly one boy? This is where conditioning is subtle. Okay. You can imagine that when C goes for a walk, if C has 2 boys and is picking one of the children to go for a walk, you could have met the first boy or the second boy, and that those are 2 equally likely scenarios. So what this does is it narrows us down to actually not 3 scenarios as it did here, but it narrows us down to 4 scenarios. Let me tell you what the 4 scenarios are. This is the intuition. Okay. So the first scenario is C has a girl first and then a boy, and you met that older boy. Okay. Or you met that younger boy. Then C has a boy first and then a girl, and you met that older boy. Okay. Or C has 2 boys, boy 1 and boy 2, and you met boy 1. C has 2 boys, boy 1 and boy 2, and you met boy 2. So there are 4 scenarios now that are consistent with you met a boy while walking and encountering C on a walk. Okay. And of those 4 scenarios, 2 consist of 2 boys. So we might suspect that this is 2 over 4. But now it's very subtle and complex. So I'm suggesting that may be 2 over 4, which is a half. But the reasoning I gave for it is very subtle and complex. And how do I know to think of 4 scenarios? What if I thought of 3 scenarios, and so on and so forth? Okay. So this is why you have to use the prescription, the mechanism, the mechanical approach to computing the conditional probability. Okay. And you should be able to get 1/2. And if you cannot, it's done carefully in the book. Okay. Now, 4th case. Okay. D is Klingon. So that was the famous sci-fi, TV series in my time. Okay, Star Trek. Okay, so D is Klingon, and Klingons always take boys for a walk. Klingon, so always take boys for walk, if it's possible. So if they're going for a walk and they're taking a kid, if they have the choice to take a boy, they take a boy. That's Klingon, maniacs. Okay. So now you met D on a walk with a boy. Met D on a walk with a boy. Okay. They always take boys for a walk. Okay. So, what are the chances that, D has two boys? Probability of two boys given that you met a boy. Okay. And now, ironically, the chances of two boys given that you met a boy on a walk is exactly equal to 1/3. So this scenario where D always takes boys for a walk is exactly the same as the scenario where I tell you that D has at least one boy. Because if you meet a boy on a walk with D, all you can conclude is that D has at least one boy. Because you know that whenever D has a boy, D will take the boy on a walk. So this and this scenario are the same. It's subtle. So you need to resort to the mechanical approach to computing conditional probabilities. It's covered carefully in the book. Okay? And you should be able to derive that 1/3 without having to do this subtle reasoning. This is the problem with new information. It can be subtle. Okay? So read the text carefully for this example, okay, and do them on your own, okay, and practice. Because conditioning is very subtle. Let me erase, and we'll come back and talk about conditional probability traps.